Hello, my dear students. In my previous lecture, I have explained the problems on steam nozzles from 1 to 3. Here, in this lecture, I'll explain the problems from 4 till 7. Now, in this problem, the steam at a pressure of 10 bar and 0.98 dry is passed through a convergent divergent nozzle to a back pressure of zero point 0.1 bar. That means the initial condition of the steam at the entry to the nozzle is 10 bar and 0.98 dry. That means it is a wet steam, that is dryness fraction of 0.98. There is a wet steam which is entering the nozzle, and finally it is getting expanded to from 10 bar to 3 bar, 3, that is 0.1 bar. The mass flow rate is 0.55 kg per second. Find the pressure at the throat. That means at the throat, what is the pressure, the exit area and velocity. So we need to find the area and velocity at the exit of a convergent divergent nozzle. And number of nozzles used if each nozzle has a throat area of 0.5 centimeters square. So we need to find the number of nozzles used if the throat area is 0.5 centimeters square. Enthalpy drop used for reheating the steam by friction in the diverging part is 10% of the overall enthalpy drop. That means here actually the enthalpy drop is occurring from 2 to 3 dash. This is the actual in the enthalpy drop with the taking the friction of 10%. That means only 90% of the isentropic enthalpy drop occurs at the exit of the nozzle. Remaining 10% is lost due to friction. So take the index of expansion as 1.13. As I said earlier, since the steam is not superheated at the entry, we need to take it as 1.13. Okay. Now, steam, first thing we need to do is, we need to find the pressure at the throat using the critical pressure ratio. So it is given as P2 by P1 equals 2 by n plus 1 power n by n minus 1. So we need the inlet, we know the inlet pressure. So using that, find out the pressure at the throat. It is P2. This problem can be solved using both steam tables and Mollier chart. So here we are solved using the steam tables. Now, first thing what you need to do is open the steam table and note down all these values, the specific volume value, HF, HFG, HG, SF, SFG, SG for all the three pressures obtained. That is the entry pressure, that is 10 bar, then the pressure at the throat 5.8 bar, and the exit pressure 0.1 bar. And we need to notice here that 1 to 2, 2 to 3, complete from 1 to 3, there is an isentropic, and it is isentropic enthalpies. That means S1 will be equal to S2 equals to S3. So, since isentropic process S1 equals S2 equals S3, we have to know the values of X1 because all these 3 points lie in the wet region. Hence, we need to find out the X1 value, X2 value and X3 value for solving the problem. But X1 value is already given as 98% dry. That means dryness fraction is 0.98. So next step is using this isentropic process, that is S1 equals S2. Similarly, S1 equals S3. First thing we need to do is find out the X2 value, that is dryness fraction at 2 and dryness fraction at 3. So first case to find x2, so s1 equals s2, that is s1 is equal to, what is s2? sf2 plus x2 into sfg2. So substitute, get the value of x2. So from this, therefore h2 equals hf2 plus x2 into hfg2. From this we find out h2 value using this dryness fraction at 2. Similarly, specific volume is obtained as x2 into vg2. So substitute x2 is 0.943 and Vg obtained from the steam tables. Substitute and get the value of V2. Next is to find x3. So we know S1 equals S3. Again, since isentropic process, S1 equals again SF3 plus X3 into SFG3. From this, get the value of X3. Once you get the value of X3, substitute, get the value of H3 as well as VS3. What is VS3? X3 into VG3. So all these points taken at point number 3. So we know how to calculate all these things from the vapor power cycles, where we have using the same method we have obtained the different values. Now next thing is we need to find out the velocity at the throat. So what is the formula? V2 is equal to square root of 2 into H1 minus H2. Here the enthalpy, there will be no frictional losses in the convergent portion. Hence, it is only 2 times H1 minus H2. Substitute H1 value and H2 value which we obtained above and get the value of velocity. So velocity will be equal to 453.9 meters per second. Then we need to find out the mass flow rate. So m dot will be equal to, at the throat will be equal to A to V2. V2 is, this is the velocity divided by specific volume. So what will be A2 equals m dot into V2 divided by capital V2. So what is the area you get? Area is equal to 3.605 into 10 power of minus 4 meters. Now, in the problem, they have given the area at the nozzle. What is the area at the nozzle given as 0.5 into 10 power of minus 4. So how do you find the number of nozzles required will be equal to total area divided by area per nozzle. Total area what we have obtained is 3.605 to 10 power of minus 4 divided by the area per nozzle what is given as 0.5. So we obtain as 7.2 and whatever above the 7. So we have to take it as 8. 8 because half nozzle cannot exist. So we are taking it as 8 nozzles. Next thing is we need to find the exit velocity. So how do you find the exit velocity? Exit velocity V3 will be equal to 2 times the actual enthalpy drop. It is H1 minus H3 dash. We can see here, right? H1 minus H3 dash. What it will be, H1 minus H3 dash will be equal to the efficiency. Efficiency is nothing but 1 minus frictional losses. So what is the efficiency? Frictional loss, they have given it as 10%. So what is the efficiency? It is 90% efficiency. So V3 will be taken as square root of 0.9 into H1 minus H3. H1 minus H3, right? So it will be H1 minus H3 dash will be equal to 0.9 times H1 minus H3. So since already we have obtained H1 and H3 values, substitute. Main thing you need to note is that you should not forget to use 10 power of 3 here. So find out the value of velocity at the exit, and it is given as, it is obtained as 1106.3 meters per second. Then we need to find out the, again, area at the exit, that is divergent exit. We need, for that we need the specific volume at the exit. So this is here directly taken from the Mollier chart for the pressure 11 bar. We have taken the specific volume from the Mollier chart. So then what will be A3 will be equal to m dot into V3 dash, that is specific volume, divided by capital V3 velocity. Substitute, get the value of area. The next problem. The steam nozzle is supplied steam at 15 bar and 350 degrees centigrade. So inlet steam condition is 15 bar and 350 degrees centigrade and discharges steam at 1 bar. So at the exit of the divergent portion, that is P3 will be equal to 1 bar. If the divergent portion of the nozzle is 80 mm long, so they have given the dimension of the divergent portion of the long of the steam nozzle as 80 mm and the throat diameter they have given as 6 mm. Determine the cone angle of the divergent portion. So I'll explain how to get the cone angle. Then assume 12% of the total enthalpy drop is lost in friction. That means how much is efficiency? It is 88% efficiency. Also determine the velocity and the temperature of the steam at the throat. So first, when steam supplied to the nozzle is superheated, we have to assume it as they are given 15 bar and 350 degrees centigrade. That means it is superheated steam entry. For superheated steam entry, the N value is 1.3. So substitute here, P2 by P1 will be equal to 2 by N plus 1 power N by N minus 1. So from this, obtain the value of P2. What will be P2 equals? 0.546 P1. So if you substitute this, you will get it as 0.546 multiply by P1, you will get it as the pressure at the throat as 8.19 bar. This problem again can be easily solved using Mollier chart. So here in this problem, we are solving using Mollier chart. From the Mollier chart, go to this 15 bar pressure where this 15 bar pressure line cuts the temperature 350 degrees centigrade temperature line. That point is considered as 1. That is nozzle entry. So that for that one, obtain the value of H1 or if you go along the x-axis, you'll find on the y-axis the H1 value. Then draw a vertical line and we have obtained the pressure, throat pressure as 8.1 by 1.9 bar. So draw a vertical line and mark a point which cuts the 8.19 bar pressure. That point is taken as H2. H2 value is taken as 2992, which it is obtained from the Mollier chart. Then again continue this vertical line till it touches the 1 bar pressure, that is the pressure at the exit of the divergent part, 1 bar pressure line. So that point you mark it as point 3. Point 3 is taken and from at that point 3 obtain the value of H3. H3 will be obtained as 2583. Now from the chart, you can say they have asked to find the temperature at the throat. So the point which is cutting this 8.19 bar lies in the superheated region. So you just check where that line cuts the temperature line and it is said to be at 270 degrees centigrade and draw a line parallel to the y-axis, obtain the value of H2. And the temperature point is cutting this vertical line with the pressure, the throat pressure line, the point number 2 is noted and that temperature is obtained as 270 degrees centigrade. Then to obtain the velocity of the steam at the throat, since here 1 to 2, it is just isentropic expansion of the steam. So V2 is obtained as a square root of 2 times H1 minus H2. So H1 and H2 values are obtained from the chart. So don't forget to multiply 10 power of 3 since it is in kilojoules per kg and the velocity is obtained as 562.12 meters per second. Then the mass flow rate at the throat is obtained as will be equal to A2 into capital V2 by small v2. So at the point 2, you need to find out the specific volume also. That volume line almost runs next to this the pressure line. So the dotted line which runs next to the pressure line, obtain the specific volume and substitute here. You will get it as it is 0.24. Then area, since the throat Dimension is given as 6 diameter. So substitute, get the area pi d square by 4. Since diameter at the throat is given as 6 so into 10 power of minus 3 whole square, get the area at the throat. Velocity we obtained here, we get the value of mass flow rate. Then velocity of the steam at the exit is obtained V3 dash will be equal to 2 times K. K is the nozzle efficiency into H1 minus H3 dash. Right here H1 minus H3 dash. This is the actual enthalpy drop. That will be equal to nozzle efficiency into H1 minus H3. So 2 times 0.88 since 12% loss due to friction. So 0.88 multiplied by H1 minus H3 value obtained from the Mollier chart multiplied by 10 power 3, you will get it as 1001.6 meter per second as the velocity. Then for to obtain V3 dash, so we need to know what is the H3 dash value. We know that H1 minus H3 dash is nothing but that is the actual enthalpy drop will be equal to 0.88 times the isentropic enthalpy drop. From this, obtain the value of H3 dash because we know H1, we know H3, we know right H1. So obtain the H3 dash value. That means this H3 dash value is obtained, this H3 dash value. For this H3 dash value, get at this point, find what would be the specific volume. Then that is taken as V3 dash from the Mollier chart. So substitute it is taken, you get it as 1.75 for 1 bar pressure and H3 dash of 2648.4. Then substitute here in the mass flow equation, you get A3 will be equal to m dot into V3 dash by V3. Substitute, you get the exit area. So what will be the exit area? From the exit area, get the diameter at the exit. Why you are doing this? We need to find out the cone angle. So to find the cone angle, now you know the diameter at the throat, you know the diameter at the exit of the divergent section. So you need using the tan formula. What will be tan theta will be equal to opposite side by adjacent side. So what is this opposite side length? That will be equal to complete D3 minus D2 divided by, because this is you have the two portions on either side, divided by half, because this half comes here, this half comes at the bottom part. So tan theta will be equal to D3 minus D2 by 2 divided by this length, adjacent side length, 80 So 80 taken as 0.08. It has to be converted into meters. So from this, obtain the theta value. Since cone angle is nothing but here theta plus theta, 2 times the theta. So cone angle will be 2 theta as 4.36 degrees. We go to the next problem. Here, the steam having the pressure of 10.5 bar and 0.9 dryness, that means it's a wet steam at the nozzle entry. It is expanded through a convergent divergent nozzle and the pressure of the steam leaving the nozzle is 0.85 bar. Find the velocity at the throat for maximum discharge conditions. Index of expansion, we know that since it is wet steam, it is 1.135. So what you need to do, you need to find out the mass flow rate of the steam through the nozzle. For maximum discharge conditions, please note this, you need to find the velocity at the throat for maximum discharge conditions. So for that, first thing you need to know, find the pressure at the throat. So pressure at the throat is P2 equals P1 into 2 by n plus 1 power n by n minus 1. This n value is again 1.135 since it is a wet steam at the entry. So you'll get the pressure as 6.063 bar. Now, we have already derived the expression for the maximum discharge. For maximum discharge, what should be the velocity? So go to that expression, find V2 will be equal to 2 times n by n plus 1 into P1 V1. This is the expression which we have derived in our previous lecture. So then, What you need to do? You need to find the V1 value. How do you find V1 value? X times it is Vg at 10.5 bar, because it is a dryness fraction. So multiply by Vg, obtain the V1 value as 0.17575. So then substitute, get the velocity V2 will be is equal to square root of 2 times 1.135. Again, just substitute here for the velocity into P1. P1 value we know, V1 value we have obtained, and you get the velocity as 443 meters per second. But we know that P1 V1 power 1 is equal to P2. Let us now find out the V2 value. Why you need to find V2 value? This we need to substitute in the mass flow rate value. So obtain the V2 value from P1, V1 and P2 values, obtain the V2 value. So once you get the V2 value, substitute in the mass flow rate equation. So area, since they are not given per meter square throat, so taken is 1 here, multiply by the velocity at the throat 443 which we obtained, divided by the specific volume, you will get the mass flow rate as 1554.4 kg per meter square of the throat area. This is the maximum discharge which can be obtained from a given dimension of a nozzle. Now go to the last problem. So here the supersaturated expansion occurs in the nozzle. So what do you mean by supersaturated? We have seen that the exact condensation will not occur on the right, so, on the dry saturated line. Below the dry saturation line, the supersaturation occurs. That line we have already explained in the previous lecture as the Wilson line. So the steam, now there is a supersaturation expansion occurring in the steam, with the steam at 2 mega Newton per meter square and to 325 degrees centigrade. This is the inlet condition of the steam. 2 mega Newton means it is 2 into 10 power of 6, right? So it's almost equal to 20 bar. And 20 bar 325 degrees centigrade. This is the entry point. The law of expansion, as it is superheated, you are taken as PV per 1.3 equals constant, and it is expanded up to the exit pressure of 0.36 mega Newton per meter square. So that is 3.6 bar. So for the flow rate of 450 kg per minute it is given. Please make sure you convert into second. So determine the throat and the exit areas. So for this you need to find the throat area and the exit area and the degree of undercooling. And as it was explained earlier that the undercooling degree occurs, that there is a drop in the temperature which occurs due to supersaturation at the exit of the nozzle. So now we need to find out the throat and the exit areas as well as degree of undercooling. So first thing, just note down what are the given data, get the P1 value, T1 and N, P3 and M dot value. So M dot is 450 by 60, it becomes 1.5 kg per second. So what is the pressure at the throat is calculated as P2 is equal to P1 into 2 by N plus 1 power N by N minus 1. Substitute, get the value of P2 value. Next, the velocity at the throat is found for supersaturated expansion. For supersaturated expansion, it was obtained in our derivation part. So V2 is equal to square root of 2n by n minus 1 P1 V1 into 1 minus P2 by P1 power n minus 1 by n. So substitute. Before that, get the V1 value. So V1 at 20 bar pressure is given as 0.132 meter cube per kg. So that is V1 is this small V1 is the specific volume. This capital V is the velocity. So substitute, you will get V2 equals 2n, P1 value we know, V1 value we know that, into 1 minus P2 by P1. So power n minus 1. If you substitute, you get the velocity of 546 meters per second. Then to get the mass flow rate, you need the specific volume at the throat. So to that, we know since it is an isentropic process, P1 V1 power n will be equal to P2 V2 power n. From that, substitute, get the specific volume V2 value. It will be equal to 0.21 meter cube per kg. Then, therefore, the throat area A2 is obtained as m dot will be equal to A2 into capital V2 by small v2. Therefore, what will be the A2 value? So, A2 is nothing but the area value will be equal to mass flow rate into specific volume divided by velocity. So, substitute, get the value of area. Once you get, then to find the next, you need to find out the exit area. To find exit area, again m dot which will be equal to V3 by small v3. So you need to find out the velocity at the exit as well as the specific volume at the exit. Right? So velocity at the exit is given. So again substitute P1 V2 here. In the previous case, you obtained as P2 by P1. Here it is P3 by P1 since we want to find out at the exit area. So V3 is equal to 864.7 meters per second. But we know that P1 V1 power n is equal to P3 V3 power n. Therefore, how do you find the V3? V3 will be equal to P1 V1 power n divided by P3 whole power this 1 by n. So P1 we know, P3 we know. So specific volume we know and P3 we know. Get the volume and specific volume at the exit. Then, but we know m dot is nothing but A3 V3 by small v3. So how do you find the A3 value? M dot value obtained in the last. Here we obtained the m dot value. Substitute that m dot value. A3 is obtained m dot into V3 by capital V3. So m dot into specific volume which you obtained here. So here you have taken P1 V1 is equal power n equals P3 V3 power n. Right? So from that we obtain the V3 value, that is specific volume value. So obtain specific value, then the velocity we obtain. So get the area. We also know that T3 by T1 is equal to P3 by P1 whole power n minus 1 by n. So therefore what will be the T3 value? T3 will be equal to T1 into P3. You can, it is just similar to the one we have already used. This expression T2 by T1, we have used the expression T2 by T1 is equal to P2 by P1 whole power n minus 1 by n, right? The same expression we are using, but for T3 at points 3 and 1. Therefore, T3 will be equal to T1 into P3 by P1 power n minus 1 by n. Substitute, we will get the value of T3. It is 402.5 Kelvin. Because we make sure that T1 value you have to substitute in terms of Kelvin, not as the degree centigrade. Then convert into degree centigrade. But as I said, there is a degree of cooling occurring in the supersaturated flows. So how to find the degree of cooling? So for the P3 value, what is the saturation temperature you need to find out? So saturation temperature for the P3 value is, that is 3.6 bar is 139 degrees centigrade. But what's the temperature you obtained as 129 degrees centigrade? So degree of cooling is 139.83 minus this 129. So 10 degrees is the cooling effect which is obtained due to supersaturation. Thank you.